This video is going to quickly run through the test, show you how I would have answered each of the problems, and what the answers should have been. Let me know if you have any questions. This first one, we are interested in graphing it. First, we have to find the y-intercept, which always comes from the last number of 10. So the y-intercept is 10. It's a polynomial, so there are no asymptotes. To figure out where it's increasing, decreasing in the critical points, we take the first derivative, which is 6x squared plus 18x minus 108, and set it equal to 0. Factor out a 6 to get x squared plus 3x minus 118 equals 0. Continuing to factor, that's x plus 6, x minus 3 equals 0. And so x equals negative 6 and 3 are going to be the critical points that we're interested in. So if we look at 3 and negative 6, and we test some points in there, testing 4 in there, in that derivative, we would have 6 times a positive, which is a positive, so it is increasing there. Plug 0 in, we would have 6 times a positive times a negative, which is a negative, so it's decreasing there. Plug negative 10 in, and we have 6 times a negative, which is a positive, so it's increasing there. So the graph is increasing from negative infinity to negative 6. Union, it's increasing again from 3 to infinity. It's decreasing in the middle from negative 6 to 3. Critical points, we have the x values of the critical points. The x values are negative 6 and 3, so we need to plug those into our calculator to find the y values. So I'll plug those into my calculator using the table feature, and negative 6 comes out to 550, and 3 comes out to negative 179. To figure out the concavity, we take the second derivative. The second derivative, f prime prime of x, going back to that first line, is going to be 12x plus 18 equals 0 to find the concavity. And when I solve that, we get x is equal to negative 1.5, or some of you said negative 3/2. That works great as well. And so again, we'll make a number line with negative 1.5 on it. We'll test something over here, maybe 0. 12 times 0 plus 18 is a positive, so it's concave up to the right. Plug in negative 10. 12 times negative 10 plus 18 is negative. It's concave down to the left. So, for the concavity, concave up from negative 1.5 to infinity, concave down from negative infinity to 1.5. The inflection point is at 1.5, comma, plugging 1.5 into the calculator, negative 1.5 it should be, sorry, we get 185.5. So plugging all this information into our graph, it's going to be obvious we need to change the scale on the x-axis. So I'm going to make it 100, 200, 300, 400, 500 going up, negative 100, 200, 300, 400 going down. The x's we can keep the same, though. We've got a critical point. Best things to graph are going to be the critical points, the inflection points, and the y-intercept, and use the rest of the details to connect those dots. So the critical points are at negative 6, comma 550, so that's way up here. The other critical point is at 3, negative 179 down here. Those are critical points, which means those are the only mins and maxes. And then the inflection points at negative 1.5 and 185. And that's where it's going to change from concave up to concave down. We know the function starts out increasing, then decreasing. At the inflection point, the concavity changes, so the rotation is going to change to the critical point and up. And that is our graph for number 1. Number 2, to find the y-intercept, we plug 0 into everything. 0 divided by negative 2 is 0, so the y-intercept is 0. For the asymptotes, the vertical asymptote, we set the denominator equal to 0, and that gives us x equals 0. For the horizontal asymptote, we take the limit as x goes to infinity, and we divide everything by x. And that gives us 3 over 1 minus 2 over x. And the 2 over x goes to 0, so we get 3 over 1. The horizontal asymptote is y equals 3. To figure out where it's increasing and decreasing in critical points, we take the derivative and set it equal to 0. So we've got f prime of x is equal to, it's a quotient, low, x minus 2, d high, 3, minus high, 3x, d low, which is 1, all over the x minus 2 squared. And when we distribute, we get 3x minus 6 minus 3x over x minus 2 squared, and the 3x's go away, so we have negative 6 over x minus 2 squared equals 0. Well, when we multiply both sides by x minus 2 squared, we get negative 6 equals 0, which never happens. That means there are no critical points. However, we do also have to consider when that denominator is undefined equal to 0 at negative 2 to decide if it's increasing or decreasing on either side of that undefined point in the first derivative. So we'll test 0. Negative 6 divided by well, let's work this out. We've got negative 6 divided by negative 2 squared is a positive. That's a negative. So it is decreasing over there. Test another one. Let's try negative 10. We have negative 6 over something squared, which is always positive. That makes it a negative as well. It is also decreasing. So it is never increasing. It is decreasing from negative infinity to negative 2, union from negative 2 to infinity. Notice we did not say it's decreasing everywhere because at negative 2 it's undefined, so it can't be decreasing there. To do concave up and concave down, we take the second derivative. I'm going to rewrite this as negative 6 times x minus 2 to the negative 2 power, so I can just use the chain rule. So we have 12 times x minus 2 to the negative 3 power times the derivative of the inside, which is 1. The negative exponent moves down, x minus 2 cubed equals 0. And again, when we multiply both sides by the denominator, we get 12 equals 0. There are no inflection points. Concavity, though, we can check at the undefined points. So we're interested in the undefined point of 2. To the right of 2, maybe we'll test 10. And that gives us 12 divided by a positive cube, which is a positive. So it's concave up on the right. Plug 0 in. That's 12 divided by a negative number cubed, which is a negative. It's concave down on the left. So taking all that information that we just learned, making sure we fill it in, we said it was concave up from, get it back on my screen, 2 to infinity. Concave down from negative infinity to 2. We said there was a vertical asymptote at 2. We said there was a horizontal asymptote at 3. We said there was a y-intercept at 0, and it's decreasing concave down. The other half is decreasing concave up. And we have our graph. Elasticity of demand. Oops, sorry, wrong problem. This is the storage problem. The storage problem, we noticed that we're doing warehouse fees based on the maximum number of widgets and per widget. So we've got both situations going on. So this is the square root of 2fm over k1 plus 2k2. F is the fixed cost of $750 to set up production. M is the total made in a year, which is 30,000. K1 is the cost per unit, and that's $1. K2 is the cost at maximum, that's $2. So when we plug that in, we get the square root of 2 times 750 times 30,000 divided by 1 plus 2 times 2. We plug that into our calculator. We order 3,000 widgets at a time. And if there are 30,000 widgets total that need to be ordered, and we order 3,000 at a time, we need to place 10 orders per year. Our next problem then is our unit elasticity. E is equal to negative P over Q dQ dP. And then we set that equal to 1 to maximize our revenue. So we have negative P over Q, which is 25,000 minus 50P, times dQ dP is equal to, the 25,000 is a constant, just negative 50. Make that equal to 1. Simplifying a bit, we've got 50 over 25,000 minus 50p equals 1. Multiply both sides by the denominator, 25,000 minus 50p. Add 50p to both sides, you get 100p equals 25,000, and divide both sides by 100, and the ideal price to maximize our revenue is $250. Part D is probably where most of the points were lost, finding dy dx. The first part, we've got a product. Think about that as a product, x to the 4th times y cubed. So the product is the derivative of the first, 4x cubed, times the second, y cubed, plus the derivative of the second, which is 3y squared dy dx, times the first, x to the 4th, plus, that's x to the 1/2, so we've got x to the negative 1/2, times 1/2 gives us 2, equals, that's y to the 1/2, so we have y to the negative 1/2. Half of 6 is 3, dy dx, and the derivative of 5 is 0. I'll move the dy dx's to the right side. That's probably the easiest way. 3x to the 4th y squared dy dx. And that leaves us with 4x cubed y cubed plus 2x to the negative 1/2 equals, and when we factor out a dy dx, 3y to the negative 1/2 minus 3x to the 4th y squared. And then divide both sides by that to find out what dy dx is. 4x cubed y cubed plus 2x to the negative 1/2 over 3y to the negative 1/2 minus 3x to the 4th y squared. And we have our solution. Part E, finding all the partials, second order partial derivatives. First, if we take fx, the derivative with respect to x, y is a constant, so we have y over the derivative of the natural log of x is x. By the way, remember I said there was a typo here. That equal should have been a plus. The derivative of 2 is 0, plus e to the x squared y is e to the stuff, times the derivative of the stuff with respect to x, which is 2xy. So we have y over x plus 2xy e to the x squared y. And the key to notice on the right side especially is that is a product, 2xy times e to the x squared y. So when I find xx, by the way, the x, we're going to treat that x as x to the negative 1 to make this easier. So it's negative y, x to the negative 2, plus, using our product rule, the derivative of the first is 2y times the second, e to the x squared y, plus the derivative of the second, e to the x squared y, the derivative of that is 2xy, times the first, which is 2xy. So simplifying that a bit, we got negative y over x squared, or you could have said y to the negative 2, plus 2y e to the x squared y, plus multiplying 4x squared y squared e to the x squared y. If we want to do fxy, we're going to take the derivative of the x with respect to y, the y over x. The derivative of y is 1. We're just left with the 1 over x, plus, again, looking at the product, 2xy. The derivative of that with respect to y is 2x times the second, e to the x squared y, plus the derivative of the second, which is e to the x squared y, times x squared, times the first, which is 2xy. So we end up with 1 over x plus 2x e to the x squared y plus 2x cubed y e to the x squared y. For the fyy, we're going to go back to the beginning and take the original derivative with respect to y. Y ln x, the derivative of that's just the natural log of x. The derivative of 2 is 0, plus the derivative of e to the x squared y is e to the stuff times the derivative of the stuff, which is x squared. So simplifying, we like to put the x squared in front. Don't really need to, but there we go. So to find fyy, natural log of x doesn't have any y's in it, so the derivative of that is 0. Then x squared is a constant, so it stays out front. E to the stuff is e to the stuff times the derivative of the stuff, which is x squared. Combining those x squareds, we get x to the fourth, e to the x squared y for our partials with respect to y and then y. Final problem on the test. We've got our cost function given to us. We're going to take the derivative of that, and the derivative of c is dc dt equals 0.2 x squared is 0.4x, and the derivative of x is dx dt. Then plugging in what we know, production is changing at a rate of 12 units, and production is x, and it's the change on x, dx dt is equal to 12. The production level is 80 units, so x is actually equal to 80. And so we have 0.4 times 80 times 12, and when we multiply all of that out, we have 384. So the cost is changing $384 per month. And that was the end of the test. So hopefully that answered some of the questions you had. Let me know if you still have any questions remaining. And good luck on the last unit.